Okay, so at this point, we've already discussed measures of central tendency. And when we talk about that, we're talking about the mean, the median, and the mode, the three most famous measures of central tendency. And we also talked measures of variation. So that is the range, which is the minimum minus the maximum, or excuse me, the maximum minus the minimum, and also the variance and the standard deviation, which I'll abbreviate SD. What we want to talk about now is a very important graph in statistics, and that is the normal distribution. It's also known as the normal curve. So the normal distribution. So if something is just distributed normally, so the normal distribution, then it's going to have this bell curve. It's also known as the bell curve. So you can hear lots of ways: the normal bell curve, the normal distribution, the normal curve. But really what it is, when we talk about the normal distribution, something that is normally distributed, you notice here in the center of the bell, we're talking about, and that should be a straight line, let's say 11. Maybe we're talking about the number of questions correct on an exam. So 11 was the most common correct. Not number 11, but 11 questions were correct. Some basic facts is that with a normal distribution, the mean is equal to the median, which is equal to the mode. So if you look at this graph here on the right, this normal curve, we're talking about the frequency. So in this case, they're talking about relative frequency, but that's still, we can associate that with frequency. 11 occurred the most, so it's definitely the mode. The normal curve is also symmetric. So it's a symmetric graph here. So I can write symmetric, which means it's a mirror image. If we were to, I can't spell today, there we go, symmetric. If we were to fold this down the middle, the left side and the right side would line up together. And it's symmetric around this 11, right, the center, which also means that the center is 11. So mode, it's the median. And also another fact is that if you were to find the mean of this, if you were to find the mean of this distribution, the mean would also equal what the median and mode are, and that is the value in the center. Okay, so that's the average. Now what we're going to use this for is we're going to look and try to find probabilities and percentages. So if I'm asking you, a question we might ask in the future is, what percent of scores, or if this case we're talking about the number of questions correct, what percent of scores received less than 7 correct? So in that case, what I would be looking for is, what percent is less than 7? So what percent of scores received less than 7 correct? So I would actually be looking for this area of the curve. And what we can do eventually is try to figure out what is this percentage. Now, in order to do that, we have to have one more fact, and that is, if we were to consider all possible scores, if we were to consider the area under the curve, so the area under the entire curve is going to equal 100%. So every value is going to be accounted for if it's in this graph. And that might seem trivial, but it's an important fact because we're looking for in the future only pieces of the area. So in this case, the entire area is 100%, which we can also associate, if we write this as a relative frequency, we could write that as 1. Now that we have an idea of what the normal curve or normal distribution looks like, we can use this to describe real-life situations. In fact, the normal curve, the normal distribution, describes lots of naturally occurring distributions. So here, suppose we knew that the mean waiting time for a doctor at Times Hospital is 10 minutes, and that it also had a standard deviation of 4 minutes. What I don't mention here, but what we're going to take and assume is that this distribution here, that the mean waiting time, or the waiting times themselves, we're going to assume that this distribution of waiting times is normally distributed. Meaning if we were to plot and create a histogram of the frequencies of all the waiting times in the hospital, it would look like a bell curve. And specifically, what we know about this bell curve is that the mean, which I'm going to abbreviate as mu, looks like a U with a little tail in the front, we're told that the mean waiting time for a doctor is 10 minutes. So I'm going to abbreviate that mu equal to 10, and in this case we're talking about minutes. And the standard deviation is 4 minutes. So I'm going to abbreviate that sigma. This is the Greek letter sigma. It's an O with a little hat, if you will. And the standard deviation is 4 minutes. What you will be asked to do is you'll be asked to represent this situation with a bell curve. So we can get an idea of where is the mean and what are the more common or less common, if we're getting further away from the mean, values that are either close or further away to the mean. So we just summarize the parameters in this situation. And what I mean by summarizing the parameters, what is the mean? What is the standard deviation? Once we have that information, we can summarize this information or summarize this situation with a bell curve. So just assume that this is a perfect bell curve. What we know about a normal distribution is that the mean is right in the middle. So in this example, we know if the waiting times are normally distributed, its graph, its histogram is going to have this bell curve, and 10 is going to be right in the middle. What we also know is that if we go plus 1 standard deviation, so if I add 1 standard deviation away, if I add 1 standard deviation to 10 minutes, so each standard deviation is worth 4, if I add 4 to this value of 10, I am now at an observation of 14 for 14 minutes. If I add another standard deviation, so if I'm 2 standard deviations away, all right, so from this 1 standard deviation, I add another one, so I'm a total of 2 standard deviations away. I am now at a value, I added 4, I'm going to add 4 again. I'm now at a value of 18. And finally, let's label one more here. Let's label plus 3 standard deviations. So if you are 3 standard deviations away, which in this case, if we add another 4, we'd be at 22. What these values are saying, and as we see here, since we're not talking, or the frequency of these observations are less, 10's in the middle, that occurred the most. It looks like if we were to compare those who waited 22 minutes with those who waited 10 minutes, obviously it's a lot less common to wait 22 minutes. So the further away we get from this mean of 10, the less common it is. Now this is if we talk about positive standard deviations away. In other words, if we are to the right of the mean, if we waited longer than 10 minutes. But we could also discuss, well, what if we had a waiting time that was 1 standard deviation to the left? So if I start with the mean and I subtract 1 standard deviation. Well, if I start with the mean and I subtract 1 standard deviation of 4, then I would be at 10 minus 4, I would be at 6. Okay. If I subtracted another standard deviation, all right, if I subtracted another one, I would be at, if I took another 4 away, I'd be at 2. And then one more if I took away, minus 3 standard deviations, well, this is going to be negative 2. This isn't very practical, is it? It's not going to make sense to have a waiting time of negative 2 minutes. So at this point, we're at a point where it's not very practical. However, everything else seems to make sense. We have a mean of 10. If we go in 1 standard deviation to the right, we're at 14. If we go 1 standard deviation to the left, we're at 6. And what we want to be able to do is describe the probability, or in this case, we want to down here talk about the percentages. So we know that the area under this whole curve is equal to 100%, right? It accounts for 100% of all the observations. What I want to know for number 3 here, so we just drew the bell curve, labeled the mean standard deviations. What I want to answer is what percent of patients at Times Hospital would we expect to wait longer than 10 minutes? When you're asked to find a percent, what you're looking for is the area under the bell curve. So if we were to draw this bell curve one more time here, I know 10's in the middle. And what I'm looking for and trying to describe is what percent of patients would we expect to wait longer than 10 minutes. So what I'm looking for is an area larger, or what area is above 10. Well, if you remember a fact about the normal distribution, you know that this 10, if it's the mean, it splits the lower half from the bottom, or the lower half from the top half. So this is actually 1/2. And if we know 100% is the area under the whole curve, then this is going to represent 50%. So that's just knowing some basic facts about the normal distribution. And that is 50% of the data or the observations are going to be above the mean. 50% of the observations are going to be above the mean. Which means, if for number 4, what percent of patients would we expect to wait less than 10 minutes? Well, if we were to draw the picture, we know 10's in the middle. What we're looking for in this problem is what is the percentage or the area to the left, or less than 10 minutes, the waiting time less than 10 minutes. So if half of the observations lie above 10 minutes, then that means 50% is going to lie below. Okay, that's just a fact that we know and that we'll use as we move forward. Here's another question. Which group is larger, the number of people who wait longer than 14 minutes or the number of people who wait less than 2 minutes? So what I'm going to do is actually label both of these on the normal curve, or on our normal distribution. Keeping in mind that I know that the standard deviations are 10. Here this was 6. This was 14. So I'm going to just kind of sketch a graph again. And it looks like actually this is the only ones that I need. 2, 6, 10, 14, 18. And this is just a quick sketch of what I drew up above. Now I'm going to label both of these. So I'm going to shade both of them. So our first question is, if we had to describe or show on this picture the number of people who waited longer than 14 minutes, that would be represented by this area, right? You are above 14. Now, if we discussed what's the number of people who waited less than 2 minutes, less than 2 minutes is going to be this area. Okay, less than 2 minutes. So, according to my picture, it looks like they're pretty close in area. However, if you look up above, there might be a better picture for us. Less than 2 is over here, and above 14 is going to be here. Notice that the observation of 2 is 2 standard deviations away. So this area is actually going to be less than. There's less people who are over here than the amount of people who were above 14. And it all has to do with the number of standard deviations away. If you are 2 standard deviations away, that's less likely to happen than if you are 1 standard deviation away. So here, if we were to compare the percentages, and actually in the future we'll be able to actually find the percentages associated with these. But if we were to compare how many people or what percentage waited longer versus waited longer than 14 minutes and less than 2, we would choose longer than 14 minutes. And we're actually going to show that on the next page. So here's a natural question. What about the standard deviations, and how do they help us find percentages? So here's a bell curve, and what's labeled, actually what you can see is the area or the percentage that lies in between those standard deviations. So what I want to do is to take this bell curve and label it with the information that I was given in the last problem. If you remember, the mean was 10, and that was for 10 minutes was the waiting period, the average, and the standard deviation was 4 minutes. So if I wanted to label this particular picture with this information, I know the mean's in the middle, so that's 10. When we are 1 standard deviation away, we are at a value of 14. When we are 2 standard deviations, we were at 18. And then when we were at another 3 standard deviations, we were at 22. So what I'm doing is just labeling, and I can write the minutes in here. I'm labeling the mean And then if I go to the right side, I'm talking about the positive standard deviations. If I go to the left, if I subtract a standard deviation of 4, I'm at 6 minutes. If I subtract another one, I'm at 2 minutes. And remember, when we went one more, it didn't really make sense, but it'll still help to put that in there. It turns out that the bell curve has some nice percentages. And if you were to describe, what percent of people wait between 6 and 10 minutes, we can look at our picture and realize that 6 minutes to 10 minutes is describing this area. And this area makes up 34% of the graph. Okay? So that's what we can use this normal curve for. Now let's answer this first question, and then we're going to use other questions and use this bell curve to answer other questions. So first, what percentage of people would we expect to wait longer than 14 minutes? So if I'm asking you to find longer than 14 minutes, we're going to go up here and we're going to shade on the picture what we're talking about. If this is 14 minutes, the first standard deviation, what we're looking for is the area between here, here, and over here to the right. Okay? So that's what we're looking for. We're looking for this area. And this isn't going to be perfect. In fact, what we're going to find is that when we move into more complicated problems, this is going to be an approximation, what we get in this problem. But on the next types of problems, what we're going to find is that we can get more precise answers. So here, what I'm looking for is the area in this block plus the area in this block. And this area is so small that we're not even going to consider it. So the area between 14 and 18 was 13.5%. So we know there were 13.5% of people had between 14 and 18. Between 18 and 22, since this is symmetric, it's hard now, you can't see it, but that was 2.5%. And again, this area is going to be so small, we're not even going to consider it. So what percentage would we actually have shaded up here? Well, if you add these together, you're going to get 13.5 plus 2.5. This is going to be 16%. So this would be about 16% of people have waiting times longer than 14 minutes. Okay, 2 more examples here. What percentage of patients would we expect to wait less than 2 minutes? So less than 2 minutes, if we go up to the chart, here's 2 minutes. 2 minutes is found right here at this number of standard deviations away. And what we're looking for is this area. We are looking for the area less than 2. And this is so small, we're not even going to consider it. So the area less than 2, if you look at this chart, it was 2.5%. So getting used to looking at the bell curve and being able to shade what we're trying to find is going to help. So here we were looking for less than 2 minutes. That's what I'm going to shade. For the next example, what percentage of patients will we expect to wait between 6 minutes and 18 minutes? So I'm going to shade that. Here starting at 6, all the way up to 18 minutes. So it's actually all of this area. We're looking for the area under the curve, and if we can find the percentage that is described in these 3 blocks, then we can describe between 6 minutes and 18 minutes. So that area would be 34%, right? And that's the area right here in between 6 minutes and 10 minutes. Then between 10 minutes and 14 minutes is another 34%. So I can add a 34% to that. And then finally, between 14 and 18 minutes, there's 13.5%. So if you add those up, if you add 34 plus 34, you're going to get 68. And then if you take 68 and you add 13.5, you're going to get 81.5. So this would be 81.5%. So in this first problem, again, we were looking for the wait time less than 2 minutes, so I labeled 2 minutes, and I want less than that, so I shaded to the left. In this problem, what percentage of patients would we expect to wait between 6 and 18? I found 6, I found 18, I shaded in the middle, and I added those sectors. Now here's the tricky part. Everything that we have done in these three examples has been exactly where the standard deviations are. So in the previous problem, we were looking at above 14 minutes. In this second problem, we were looking at less than 2. And here we're talking about 6 and 18. All of these values are occurring at values of exact number of standard deviations. So what's going to happen is we're going to be asked questions about the standard deviation, or excuse me, about an observation that is not exactly 1 or 2 standard deviations away. So what do we do in that case? Let's see. So on the last page, I posed this question. What if we aren't given the exact number of standard deviations away? In other words, what if I ask the question such as, what percent of people, or what percent is above 16 minutes? Or what percent of patients waited longer than 16 minutes? Well, if you look at the chart here, 16 does not occur exactly at +1 standard deviation or +2. It actually occurs, if I were to label 16 on this chart, 16 occurs between 14 and 18. So my question is, well, how many standard deviations away is an observation of 16? I know it's not 1. 1 only gets me to 14. I know it's not 2. 2 standard deviations is too far. So just knowing that, I know my observation, or my number of standard deviations has to be between 1 and 2. It has to be somewhere between 1 and 2. Now let's think about this. In order to find out the number of standard deviations, what I need to consider is, well, what is the total distance between my mean and my observation? So in other words, how far is 16 from my mean of 10? So if I take 16 and I subtract 10, I'm going to get a value of 6. So I know that my observation is a value of 6. It is 6 away from 10. I know it's not going to be an even number of standard deviations because each standard deviation, remember, my mean was 10 and my standard deviation was 4. So I know at a value, if I was 4 away, I would be 1 standard deviation. If I was 8 away, I was at 2 standard deviations. So what I can actually do is to take this value of 6 and divide it by the size of the standard deviation. So I first figure out how far away is it. Then I divide by the total number of standard deviations, or excuse me, the size of the standard deviations. And if you were to divide 6 and divide it by 4, you're going to get a size of 1.5. 1.5. So the answer to this question, how many standard deviations away is an observation of 16? I would be 1.5 standard deviations away. If you waited 16 minutes, you would be halfway between 14 and 18. You are 1.5 standard deviations away. What we just found is a z-score. A z-score is associated with how many standard deviations away are you from the mean. And the formula is actually exactly what we just kind of derived here. Is our observation, and we're first going to figure out, well, how far is our observation from the mean? So we're going to subtract those two values. So take our observation, in this case was 16, we subtracted our mean 10, and what you're finding is, what is the absolute distance between those two? And then we're going to divide that by the size of the standard deviation. So you're going to divide that by the standard deviation. And this is just writing this in words, so the standard deviation. If we were to write this in terms of symbols, my observation is just some x value. I'm going to subtract the mean, and I'm going to divide that by the size of the standard deviation. So this formula is telling us and normalizing, if you will, an observation. How many standard deviations are we from the mean? Once we have this amount, once we figure out how many standard deviations we are away, we can look at what's called a z-score chart. And the z-score chart, z-score, I can write, there we go, z-score chart. And what the z-score chart is going to do is it will go between not just regular +1 standard deviation +2, but we might be able to go from this case, if we have a z-score of 1.5, we can use our z-score chart, and what our z-score chart is going to tell us is the area to the left. The area, in this case, the percentage to the left of that observation. So the z-score chart is going to allow us to convert between how far are we from the mean and what percent lies below that observation. That's going to be in a different video. That's going to be it for this video because it's getting to a pretty long video. So let's now, if you want to go on over to the second video that's associated with this lesson, we're going to be getting into that.